required some somewhat substantial changes to them before we printed them. All right, so I thought I would just say a few things about the posters before we get started. If you look at like the actual document for the project, there's a whole section down here on what should go into your poster. Let me just say kind of, so just highlight a few things. So first of all, there are like two types of posters out there, right? If you're working in like biology, a common thing to do is to have a poster which is basically your whole research report paper. It has whole paragraphs in it in small text, and people could download it online and kind of reconstruct exactly what you did. Maybe they can spend half an hour there reading the poster by itself. Don't make this type of poster, okay? The other type of poster is one where your goal is to stand next to it and explain what you did to someone, and the whole interaction that the person you're explaining to has with your project is that time at the poster where you're standing there with them, right? So it's mainly you explaining with your words, but you're using the poster as kind of as a reference. You might want to kind of, it might have some bullets so you remember what to talk about. It hopefully has some useful pictures and charts that you can refer to, but does not have a lot of text. If there's a lot of text on the poster, no one's going to read it, okay? I'm going to come around and look at your poster. I think I've got 2 or 3 minutes per poster. I'm not going to read a lot of text in your poster, okay? Other people in the class, all of you are going to be assigned to look at two other posters, and you're going to go and talk to those other posters, people who are presenting them, and maybe spend 5 to 10 minutes talking with them. You will talk with the other person and the group there and look at the poster. You will not want to be reading all of the text, right? If you were at the poster, would you want to read a big paragraph of text, or would you rather talk to someone? Probably you'd like to talk to someone. Now, I mean, a few of you may just want to look at the text and not speak to people. That's fine, but for the most of the class, we'll aim it for the other way. You're also welcome, and it will be encouraged to look at posters who you are not specifically assigned to go read, and you will all vote on which poster you think is the best. Okay? And so you're encouraged to go look at all of them. The ones that are the best are typically not small font. They're going to be ones that are creative and interesting, have cool designs and stand out, and the project is cool, right? So these are what you want to make your poster like. Okay, so I've got some example posters up here, the same one we had at the beginning of the semester. You're welcome to come take a look at them after class. I'll have them up here for a while. I'll probably try and bring them back on Wednesday as well, just kind of as a rough idea of what the posters should look like. I'd rather you guys use your imagination, right? Cool posters in the past have brought in visual or some audio aids, right? So they've gone beyond just putting stuff on the poster up there. All right, so now some more specific details. You can see a succinct title and names, the same as your final report. Again, what is the problem and data you worked on? This should be the first thing that comes across. What were the key ideas, right? Again, I want to bring out these key ideas so people are engaged and interested. And then, just for my sake, what I want to see as I'm coming around, I want to be able to pick out what techniques you applied from class. Okay, so that's what I'll be looking for when I'll be coming around, so make sure that's on there. And then what did you learn, right? You learned something from doing all this experimentation and work on stuff, share that with everyone else. Okay, so those are the main things, but make sure to have big, pictures and charts. One other thing to show you, so Sunipa got this. This is, there's some stuff that's cut off here on the top. There you go. So this is a school computing template. This is a PowerPoint slide, a single PowerPoint slide. I think I'll allow Sunipa to post it on Canvas if she hasn't already. You're welcome to use this. You know, your poster won't stand out if you use this exactly, but that's fine. It looks nicer than just a blank template. There are a bunch of good things going on here, though. Okay? It's got a thing for the title at the top and then the authors. You don't need to have your department and the university. Okay? You probably don't need references. You could have acknowledgments, but this stuff can be small and at the bottom. So you don't necessarily need to have this. Okay? You don't necessarily need to have a big abstract, but an introduction is good. The idea of having 3 columns is often very good. At some point, about 5 years ago, I ran some poster session for the department, and I brought in like a graphics designer who like made posters kind of as a part-time job as he was going back to school. And he said, you know, there's something kind of magical about 3 columns. It kind of works well. And you know, I try and put like a big picture or something that illustrates what the main idea is going on in the middle column to really pull someone's attention. Have this be the introduction motivation, and then everything else about the techniques that you use and what you learn. And kind of make it sequential from the first column to the second to the third, and kind of it hits kind of an apex of interestingness in this order when you reach some critical thing, and that's also the middle of the poster, drawing your attention, saying, this is what's really cool about the stuff I've done. Okay, so this is just some general guidelines for making posters. Okay, you don't need full sentences on your poster, right? 1 or 2 full sentences is okay to set up some motivation, but you can have bullets. They can be short and brief. You know, one also thing, this font is not perfect, but you generally want sans serif font. Who knows what sans serif font is? Who knows? Okay, so who's never heard of this before? Okay, so if you look at a font, the serifs are these little loop-de-loop things that are added onto letters. This is great if you're reading like a newspaper. It actually helps read a little, I mean, not crazy ones, right, but just a little bit. So if you look at the New York Times font, it has some little serif, some little extra little turns and stuff on things. For posters, you want to read stuff from further away and catch the main idea of big attention, like headlines, then you want a sans serif font. Sans means it does not have these little twirly things on here. So like things like Arial and like Helvetica are kind of the typical sans serif fonts. There are other ones that are fine too. Some people like Comic Sans. There's some groups in our department who like to use Comic Sans for their posters. I'm not a big fan, so, but you know, if there's a reason for doing it, your poster is about clowns or something, then that's great. Okay. So someone wants a poster analyzing like newspaper articles, and the whole thing looked like a big newspaper, right? So you know, you can go wild with ideas like that. All right. Okay, any questions about posters? Okay. Oh, yep.
Is the dimensions, is it like landscape or portrait?
Yeah, you will get to, you can print either way. We will present some easels and poster board. We will print them at 3 feet by 2 feet. So it's not a huge size, the same size as these posters. You'll go to poster sessions and they'll be like 4 by 6, which is like twice as big. But 2 by 3 is plenty big for this. It's much easier for us to print. So the department will print the posters if you make them as like a one big sheet style. You're welcome, if you feel uncomfortable doing this, you're welcome to make like 8 PowerPoint slides and then print those yourself and tack those up. That's okay. Like, I'm not gonna, if you want to do that, that's fine. I recommend you try and do this. It'll be, almost everyone does this usually. But there'll be deadlines. If you miss the deadline for printing, you either need to go to Kinko's to print it, which will cost you like $50, or you can do PowerPoint slides. If you do by the deadline, we'll print it for free. It doesn't cost us that much. Kinko's is a for-profit company. So this is one of the places where they can print it and you can't unless you have a poster printer. So they can charge you $50 for it. Okay. It might not cost that much. All right, so let's see. Okay. Oh yeah, one more thing. Yeah, so the end term test is a week from today, next week, Monday. Be in class. Everyone needs to be here for the end term test if you want to take it and get credit for it. And I can talk more about it Wednesday, but we'll roughly cover the second half of the semester. Spring break came partway into the second half, right? So roughly the stuff that was not covered on the midterm and since then. Okay, so it could be anything, but it will focus on the stuff, mainly after the midterm. Okay, and it'll be just roughly the same as the midterm in style, length, and hopefully the difficulty. Maybe a bit easier, but it's hard to know until you take it. Okay. Questions? Oh, okay. Oh, yep.
Do we know yet when the poster submission deadline is for printing?
For printing, probably, let's look at the schedule. It'll probably be, so this May 2nd, usually need about a week, so it'll probably be early next week. Maybe I don't have it the same day as the end term. So I'll have to work this out with Chris Coleman. So I would aim for Wednesday next week, is my guess. Okay. Yeah, but I will figure that out in the next few days, and I will update the project PDF, and I'll post on Canvas about that. Yeah.
Then what's the deadline of that poster outline?
So you need to submit a poster outline on Canvas. I believe it's, I'll have to check what it says in Canvas. I think it says Thursday at 5 p.m. I might push it to Friday at 5 p.m. But I think Thursday at 5 p.m. should be fine. It just needs to be some outline of a draft of your poster. If this date is not good for other deadlines, let me know. It's a bit flexible. But I want to make sure you don't do it at the last minute. We need to approve it before we allow you to send it to be printed. I don't want you to have to print it twice, and I don't want you to print a really poor poster. Okay, well, I want you to do a good job. There's not a lot of places where you get training in a computer science department for like how to do presentation, how to do communication, and this is really important if you work as a data scientist. So hopefully we'll give you some useful feedback here. I'd rather not just completely blow this off, just do it. Okay, great. Okay, so the rest of today's lecture is going to be on so MapReduce, distributed file systems, and then how to compute PageRank at scale, which is what we talked about last Wednesday. Okay, so who's heard of PageRank before the start of the class, before the start of the semester? Okay, and who took the class because they want, who's heard of, let's say it again, who's heard of MapReduce before the start of the semester? And who took the class because they want to learn more about MapReduce? Okay, good. Okay, this is better than last year. Last year, fewer people had heard of it, and no one took the class because they wanted to learn about MapReduce. When I started teaching this was most of the class. Most of them, people wanted to learn about MapReduce. That's why they came and took the class. As I'll explain in the lecture today, it's kind of, it's not as I think it's still an important part of the kind of the fabric of kind of large scale mining of data, but it's not like, oh wow, this new thing that no one really understands anymore. I think it's kind of understood, and it's kind of been replaced to some extent. I'll talk about the parts of it which are surviving in other systems. Okay, so before we talk about MapReduce, I want to start talking about big data, and then how this led to data science. And as Kevin heard last Thursday, kind of there's this paradigm shift in how people looked at sciences in general, from like, so kind of MapReduce came about as infrastructure to support the way of doing science from a data science perspective. Okay, so I know when I was in high school, and maybe when all of you were in high school, you learned about science using this sign of the classic scientific paradigm, right? And so if you remember how this works, you would say, one, I'm going to make make some hypothesis about the world, right? You have an idea, right? You don't explain where this is coming from, but it's supposed to be coming kind of just out of the ether. And this is slightly past the time when people believed in ethers, but this helped them believe there wasn't ethers. Okay, and then the step 2 is you go and you gather data specific to try and understand whether this hypothesis are true, and then you would check, and then step 3, check if data supports the the hypothesis, right? And so most of the field of statistics was developed to answer this question, step 3. This whole process kind of existed for about 200 to 300 years of thinking about science this way, where you make a hypothesis, you gather data to try and support it, and then you kind of check whether the data supports it. And about 100 years, people started formalizing statistics as a formal way of trying to check whether data supported a hypothesis. Okay, did anyone learn this in high school or did a science fair where you had to follow these patterns? Right? So this is kind of a very ancient, and it like really served its purpose because it kind of really formalized how to do science in a nice kind of and rigorous way that kind of avoided a lot of fallacies about it. But data science operates on a kind of a different view here, where you start by step 0. There exists some large data set, and this starts before you do anything, and then you just step 1, and it's the only step, is you search for some sort of interesting hypothesis or pattern which is supported by the data. Okay? So instead of forming a hypothesis, then gathering data, then checking if that data supported the hypothesis, and these needed to be separate for the statistics formally to work, we now say we start with some existing data set that we found on the web or in some carefully gathered corpus, like the mapping of the human genome or something like that. And then we try and look for some pattern or some hypothesis. We do clustering, dimensional reduction on it, do regression, classification, and we check if it's, if that looks meaningful, then we say, okay, cool, right? We found something interesting, and we know the data supports it because we found it in the data. Some interesting pattern. We have to be more. There are some challenges with this. Cross-validation is a really important tool in this space. Okay. So this is kind of a different way of thinking about doing science, but it starts with there exists this really large data set, and before here we typically gathered fairly small data sets. We didn't need to worry about the infrastructure behind this anymore. And how do you deal with this and access this big large data set? So this is what distributed file systems and MapReduce kind of really allowed to work well in the internet kind of part of the data gathering world. Right, so at Google specifically. Google gathered lots of data about the web, about your own search history, about the own things that you like to email about so they could serve ads on. They gathered lots and lots of data. They want to use this for kind of discovering stuff about what are interesting pages on the web or what are good things to sell ads about. Right? But they collected this data set separately from trying to analyze it. which is different than the old paradigm. Okay, so so the key foundation to this, which came before MapReduce, was this idea of this distributed file system. And so inside of Google, it was called the Google file system. Inside of Hadoop, which is the open source version of MapReduce, it's called the Hadoop file system. There it's called HDFS, or Hadoop Distributed File System. You know, and this kind of paradigm has definitely lived on beyond MapReduce itself. Okay, and so prior to kind of this sort of stuff, either people stored data in a very specialized file format that everyone made up their own, or they used these kind of large-scale SQL databases, which were very, very rigid. Okay, and so distributed file systems attempted to build infrastructure as stable as SQL, but a much more flexible format for storing stuff. And everything in the distributed file system so fits as a key value pair. Okay, so what this means, the key kind of tells you an identifier of what it is, and then the value stores actual data. Right there, you know, depending on how you do this, if you have like various JSON formats or something like this, that can essentially you can put some sort of hierarchy into this. But at the basic level, you think of I'll write some examples. But this is much more general than what was a traditional SQL file system. So it can be a log ID, and this is the log. So if you have an error, you run a program, it outputs a log of all the print statements. You have each line of it gets an ID, and then you actually get the statement of the actual log as the value. You can have the web address as the key, and then you can store in the value the HTML. You can store the outgoing links. These are stuff that's important for running these search engines, right? So the web page, you might want to list on your search engine all the information you need to kind of predict whether this is useful, at least from that search engine. It could be the ingoing links too. You could store other stuff there, right? You could store a document ID, like a page on Wikipedia, and then this might just be the list of words which are appearing on that page, right? Or you can do something like a particular word, and then how many times, say, and where it appears in some data set, some corpus. Right, so it's fairly flexible, right? These are kind of the opposite of each other. This one, you have a document ID, and then whatever is in that document, and this one is the word, and it lists all the documents. You can kind of reverse these back and forth, right? And we'll go through some MapReduce examples looking at these sorts of objects a bit in this lecture. Okay, so, but it's a pretty flexible file format, and this was, you know, in the early 2000s, this was starting to come up a lot and didn't really fit in SQL format, but there were data sets so big that they did not fit on a single computer. Okay, they were too big to fit on a single computer, so we needed to think about how do we deal with this in some way that's easily parallelizable. So they want to build a system that can handle this sort of data, and it was made sense to parallelize it. So it had to be not too specialized so they could use it for lots of different sorts of problems. Okay, and so when you have really big data, okay, what you basically typically want to do is to store in some blocks of data. So each block is going to contain a bunch of key value pairs, and this will be size of roughly 64 megabytes as count. Right, so it could store a fair amount of data in here, but like this is not, can be not just, there can be terabytes of this data, and it's broken down to these block-sized chunks. Okay, and each chunk will, hopefully typically each object in here will fit within a block, and often you can fit a bunch of these inside a single block, but then we'll have a uniform roughly size of 64 megabytes that will think in kind of storing each of these by itself in terms of these blocks, not at the level of the key value store. So this allows the system to always have roughly this size for the blocks it moves around, independent on how big any particular key value pair is. Okay? And then what might be interesting about this is that it's then going to say, I'm going to make 2 to 3 copies of each block. Okay, and I'm going to store each copy on a different computer. Okay, so I've got a big distributed set of data that I cannot fit all in one computer. I need to store it across many different computers. And so I'm going to break it down to these blocks, make 2 to 3 copies, either 2 or 3, and that's consistent across the system typically. And then I'm going to store each copy on a different computer, and basically at random. Okay, so 2 blocks. Let's say I have a data set, and I'm just reading off pages on Wikipedia, and I have all the pages about like the pro wrestlers and the different pro wrestlers. Apparently, there's a big part of Wikipedia about pro wrestling. Because some of the most edited pages are about pro wrestling, and so there may be these don't all fit in one block. But I'm going to break them into blocks, and then I don't necessarily store them next to each other. Right? I'm eschewing the use of locality of these blocks. So most database systems try and say, if these blocks are similar to each other, I want to have them near each other. I want to access them in sequence. They're right next to each other on disk. If I read one, I can read the next one. This is more efficient. This is doing the opposite. I'm storing them basically at random on different computers. Okay? And this was this was first looked at as kind of strange, right? Why would you store them, similar things not next to each other? Why would you get rid of locality, right? So, why is it okay to get rid of locality? Yep.
Some sense of resiliency. If someone tried to hack your data, they couldn't get to all copies of it.
Yeah. So resiliency is good. Not for the hacking sense, although this fits with some stuff later. But definitely resiliency is the reason.
Can you read similar blocks at the same time? Or
yeah.
Blocks at the same time?
Right. So there are 2 reasons. So why little locality? So the first one is resiliency. So these were initially really big systems where and then I'll say redundancy. Okay, so which are slightly different. So the reason for resiliency was not because of hacking. Later, these things show up for different security and obfuscation reasons, but we won't get into them here. The reason this was interesting is when Google was a startup, there are these pictures of them sitting in their office in grad school in Stanford, where they had all these old computers, every old computer they could find that was up and running, stacked around the room, all different types of computers. Where the big thing at the time was to get these mainframes from Cray or something that could run one really fast computer. And this is coming back with deep nets in some places, right? But at this point, they were kind of a cheap startup. They're like, instead of one really fast computer really big, we're going to have a bunch of cheap computers, and sometimes they're going to crash, right? So computers, especially in the early 2000s, I don't know if you remember running Windows or whatnot, they would crash all the time. Okay, and so if you're running 1,000 of them and you need a big parallel process to run 1,000 computers, if you run them for a couple hours, probably one of them is going to crash. Or it's not going to crash, but it decides to do some garbage collection. Who knows what it's doing? It decides to reboot. It goes down for a while, right? So with the resiliency, so if a computer goes down, there is another that can take its place, right? So maybe it was hacked, but more likely just there was something happened and there was a short circuit and something crashed, and this happened, right? So they were running these at scale, and if something went down, it could automatically recover from this. Okay. Then there's the other thing with redundancy that if I have a huge data set, I only want to look at part of it, then I can read part of it on each different computer and send that back to a main server. I don't need to read through the entire hard disk on one computer. I can split. I can basically split the read time across the cluster. So I can basically read stuff in parallel, right? If you have a huge data set, one of the challenges on your hard disk is that it could just take like an hour or two just to read all the data, right? So if it's distributed and you have to read 1/20th of it across 20 computers, it takes 1/20th as long, plus some overhead for sending it to a server, right? So both of these made it kind of were advantages about getting rid of this locality. Yep.
When you said that we have 2-3 copies of each block, is it like exact copy or
Yes.
similar data?
So typically you would say this data gets in this block, whether it's one document or 5 or 6 documents that fit in that space, and you just make exact copies.
So if it's exact copy, then how is redundancy relevant? Because I don't want to read same data from 6 different sources.
Each block is pretty small, so if you can read a block pretty quickly. A block is pretty small scale. It's big enough to contain at least one key value pair typically, often more. But if you're reading like all of the Wikipedia on pro wrestling, that probably fits across 100 blocks.
But those 100 blocks are not exact copy.
And they're all exact copies. So I take the 100 blocks worth of data on pro wrestling, and I break it up into 100 blocks, and each of those I make 3 copies of. And then I store them in random places on my cluster. Right? The other reason for this that you've kind of touched on, heterogeneous. Okay, so different data is going to have different sizes and formats. Sometimes, each key value pair is a whole article on Wikipedia. Sometimes it's a tweet, which is much smaller. If it's a tweet, I can fit, I don't know what the number, I can maybe fit hundreds, if not thousands, into a block. And Wikipedia articles, they might be really long. I can fit just in the tens to dozens of them into a block. So by doing this, I can kind of fit different types of data. I don't need to specialize it too much to the type of data. This block kind of seems to be a good size for handling different types of. I don't want to typically split data up across 2 blocks, but I don't want it to be too big either. I want it to be relatively small, but not have to often split one data point, one key value pair across multiple blocks. Yeah.
So given all of this, would you assume that there are very infrequent updates?
Yes, right. So typically with this, you have Yeah, so let me add some things. You have, so you have infrequent updates, and mainly, most of the updates are just appends. Okay? So if you look at the pages on the web, right? Most web pages, like I have my web page and the web page for the class that'll update a few times a week with small tweaks. Most web pages are not like that. They're like news articles, right? They write the news article, they publish it. Most of them don't need to be updated, right? So that you just keep getting more and more data that you do. People, I go onto Google and I make some searches, right? I can't go back and edit my old searches. I can only do more searches, right? So I'm just appending data right here. So if I append more data, I create a new block, I go and store it someplace, right? Now the order that these things came in, I don't want to go back and sort things by order so I have locality that way. I don't want to have to worry about maintaining something like that.
Okay, sorry, second question. So also, like, is there any sort of index or search structure on top of this, given the kind of random locality?
So what you would typically do is MapReduce is how you'd interact with this storage system. And it's kind of not a great search structure. If you may build a separate search structure which you occasionally rebuild from scratch. It's typically what you would do. Maybe you would do updates to it, but you would, so I think Google would just occasionally just rebuild its index over. Originally, they would PageRank and rebuild the index like every night, is what they would do. Or maybe it was every few nights at the beginning. Right now, they do stuff so they can figure out how to update it. They've gotten kind of past this so they can handle updates more efficiently. Yeah, but originally that was not the case. So in the original design, that was not the case. Okay, so this is kind of the idea of the distributed file system. You'd store data, really large data, this way across thousands of machines. Machines go down, it's going to be resilient to it. And that was the big difference in how they built the hardware side, was cheap machines that would crash a lot. And this was kind of a file system that it just kind of worked. They build it and they can use for lots of type of stuff. They can fit into this key value pair kind of version, and it worked. And it mainly infrequent updates for this sort of data. Yeah. So there was like an article, there was like a blog post about MapReduce, a giant step backwards from some very well-known and kind of smart database people, which they kind of walked back over the years. But then a lot of things they ended up saying in that article ended up being what MapReduce evolved into. Okay, which is the system that's, in order to do searching on top of this, you often use MapReduce, which I'll describe next. Okay, so MapReduce. Okay, so MapReduce is a way of interacting, doing queries over a distributed file system. So queries over the distributed file system, and usually they're interesting when the output is large, right? So the output is something that you might not even want to store on one computer. This was, originally you could do queries where the output was small on MapReduce, and that was the best way to do them. But this was one of the first things that was kind of replaced with something better, where you could do outputs that are small. MapReduce made the most sense when the output was roughly as large as, on the same order as the input. And we'll see some examples. It's more of a transformation of the data or like a view of the data than a query returning a small subset. Okay, and so MapReduce will have 3 or 4 parts, and the first one is called map, right? And the third one is called, a little bit lower, is the third one is called reduce. This is where it gets its name. Typically, these are the only two steps that you have to write in a query. There's another step that comes inside of here called the shuffle, which is implemented as inside the MapReduce system. You don't have to do this. Okay. So the map phase. The map phase is a transformation of a key value pair into another key value pair, where it's useful to either group or sort on K prime, right? So K prime is the key of the new key value pair. Okay, so I'm taking the key value pair and I'm transforming again in my, everything is stored as key value pairs, but now the new key is something that I want to group things by, right? So if I want to find all of the Wikipedia articles that list someone with the name Jeff, right? Then I would look at each key value pair. If it contains the word Jeff in it, I would put the key prime as K prime as Jeff, and then the value of everything else about the article that I want to do something about. Right? So I want to group all these by if they include my name in it, right? I'm very vain about something like that. Okay. Okay, and then the job of the shuffle is to put all K prime V1 and K prime V2 with this same K prime on the same computer. Okay, the shuffle works behind the scenes. Everything that has the same key and the output of the map step will be put on the same computer. Okay, and then the reduce step, I'm going to, and so this is the same here. Okay, the reduce step is going to take all these things, K prime V1, K prime V2, and it's going to map to, you know, some output set. Let's call this K double prime kind of V. And so V is going to be a function of V1, V2, and so forth. Let me write this a bit more clearly. So that outputs some new key and some new value, which is going to be the output, typically a V1, V2, V3, Vn. And so these are, all of these guys here are going into this function, right? So I'm going to take all the data that's been passed, that's been grouped by this key, and I'm going to compute something new here. This is whatever my output wants to be. Okay, and so occasionally I might do a couple of rounds of this. I might chain together this, where this is now the input in the next round. But in the early days, in the examples we'll look at, this will be done in just one round, where we have to structure the query in this way. There's some things you want to do, like if you want to run like Lloyd's algorithm, you kind of iterate on the data in certain ways, and you need some number of rounds. And you kind of want to minimize the number of rounds, and I'll come back to why that's the case. Okay, there's one more step that's sometimes in here that's kind of optional. 1.5. There's a combined step, and this is optional. Okay, and the idea here is that you somehow all the keys all the key value pairs which are coming out of one computer, you might do some pre-processing before the shuffle step. So this is pre-processing K prime V1, K prime V2 on same computer before doing the shuffle. Okay, so the shuffle is going on behind the scenes and is where most of the runtime takes place typically. Well, actually, sometimes it gets broken up, but this is where all the data is moved across this distributed file system. Is completely done in the back end. It's often typically done by just assigning keys randomly to different computers, each of the K primes randomly. Is the basic implementation of this. But this is done behind the scenes, and if things crash, it automatically figures out where it sent something and then recalls one of the copies of it and so forth. It does some duplication here for some robustness stuff, but this has gone on behind the scenes. If you don't want to send as much information because you may have some duplicates or can pre-process some of the step, you would do this as part of the map step. But these you can think of as running like a stream over the key value pairs, the initial part, and then before you run the shuffle, you pre-process the whole output before this sends it across computers, and then this is the post-processing. Okay, let me go through a couple of examples, and then I'll talk about some implementation notes, and then we'll talk about doing PageRank in the system. Okay, any questions so far? Maybe an example will help. Okay, so the typical example is like the hello world of like MapReduce is the word count problem. Okay, and so what you need to think about is you have stored in the DFS, you have a huge text corpus like the English language part of Wikipedia, and the goal is to count for every word how many times it's used across the whole corpus. All right, so now again the output is large here, right? The input is large and the output is large because every word I need to have a count. Right, so it's not like a small query, you would just return how many times has the word happy occurred. I want to count for all words. Okay. Okay, so how do I do this in 2 steps? I need to write the map and the reduce. All right, so I'm going to read through each of the text corpuses. So I'm going to read text, and so for each word W in text, I'm going to output a tuple W1. So this is that word and the number of times it occurs, which is 1. Okay, then on this is the whole map step. I just read and create these tuples, and I kind of print them out into the MapReduce, and then it queues them up and shuffles them, right? And then this reduce step is going to take as input for some W. It's going to have a list W V1. W V2, W V3, and so on. And so then the output of the reduce step will be
W in the summation of these.
yeah, so it's W and then this summation of these VIs. Right, so I just add up all the values. And this is the reduce step, this is word count. Okay, so in order to do this, even though the data is huge, it's distributed, I can just write a couple short snippets of code, and it will take care of all the distributed back-end processing for me. Okay? Great, so this was pretty easy. There's one problem. This does not work. Let's say I needed to put, let's say my data set was so big that I needed to split it across, let's say, at least 20 computers. Right, if I need at least 20 computers. Let's say I need at least, say, 20, maybe 50 computers. Something's going to fail here. This doesn't quite work, and then there's a simple fix. Right, so the shuffle I don't have to worry about. This is the right map and reduce step. What's going to go wrong here? Remember when I talked about the noise lecture, I talked about these heavy tail distributions, right? And I was kind of running out of time, but I mentioned that text kind of follows this, this law called Zipf law, where some words are very popular and then they drop off at a polynomial rate, right? The word, right? So the word the occurs 7% of the time. I think it was on, I forget exactly what the words were it's like 3.5% of the time, and like or it was something else was 2.8%, right? And these kind of decayed at a polynomial rate. Yeah, so what happens if I run this on a large amount of text?
The reduce may not fit in the RAM of a single computer.
Right. The computer I map the word the to is going to require 7% of all the data. Right? And remember, I need to split it across 20 or 50 computers. That means I can only fit 5% of the data if it's 20 computers. Or if it's 50 computers, I can only fit 2% of the data on any one computer. So the one that gets the word the is going to crash. It's not going to work, or it's going to thrash, or something's going to happen. Right? So this isn't going to work. This is so I need to do something else. So how can I easily fix this? What's the other step I can sometimes optionally do? I can do the combiner. And so what should I do on the combiner? This is going to take all of the words v1 or word v2, and it's going to output word the sum is 1 to n vi. Right, so I'm just going to sum up this for each word that's coming off each of the computers before I do the shuffle step. Then I know at the reduce step, no matter what the word is, I have at most one tuple from each of the computers, or maybe from each of the blocks. Maybe it combines it on a block level. Okay, and then there can't be too many, and this won't crash. So by doing this combiner first, for words that are fairly common, I might not do anything in this combiner phase, but for the word the, that's going to occur 100 times on average Wikipedia article. So I'm going to save my communication a lot, and I'm going to avoid this problem of crashing. Okay. All right, so let's, so this is often known of the problem here when you have a bunch of stuff. Even if you overload one node, even if it doesn't crash, there's something known as the curse of the last reducer, right? And this happens in a lot of parallel algorithms where you split some tasks up into a bunch of different computers, and then you have to wait to be done until they all finish running, and most of them are done. On average, they're fast, but there's one computer that gets the word the or something else painful, and that one takes a long time. And so the curse of the last reducer is when everything's finished except one computer is kind of a straggler. Okay, so if this is because the computer's crashed or has not responded, MapReduce, or the system, will automatically figure out how to outsource, redistribute the computation that was assigned to that computer to all the other ones which are idle. But if it's because of this problem where I put too many words in one computer, then there's nothing MapReduce itself can do. You have to do something smarter with the combiner or design your algorithm in some way that's more intelligent. Right? So there are these algorithms for counting triangles and graphs that kind of had some algorithmic breakthrough that allowed, figured out how to, through a small number of rounds, get rid of this sort of issue. Right? And it was thinking about how to design the sequence of these MapReduce queries so that they could do this without ever overloading one of the nodes. In graphs, the issue is one of the vertices may have a huge degree, and so when you process that vertex, it takes a long time, where most of them process really fast. And this happens in big, like, social network graphs, like everyone's following the like Kardashians on Twitter, so they have way more edges than I do on Twitter. So it's probably for the best. Okay. I want to say one more thing, because we won't, just before I go on with another example, there's an issue about the number of rounds. So there's some algorithms, like think of like Lloyd's algorithm for k-means. When MapReduce first started becoming popular, you'd see there's some blog post that says, okay, let's do another kind of data mining example. Let's run Lloyd's algorithm for k-means. And they did it where each round was basically doing the assignment step to everything to the best center, and then the redoing of the center, and that was a full round of MapReduce. Okay. Originally in MapReduce, and the same was true inside of Hadoop, and it is still somewhat true, is the problem is the rounds are slow. There's overhead, and this is because they write everything to disk each round. Okay, so part of this is passed over the network, but when you get output of the reducer, it stores the output of this back on disk. Even if you set something up that intentionally has multiple rounds, you need to do it. Every time it sets it back to disk, and it needs to do that for the redundancy, for the issue with resiliency. These nodes would crash, and in order to recover from the crash, it needs to be written back to disk and to know when it was written back to disk. So each round had an overhead. It ranged, depending on the system and the setup, it ranged from a few minutes to it could be like dozens of minutes between these rounds. Okay, if it was a really slow system where it had to boot up the JVM every time it initialized a round. And so the rounds were really slow, and you really tried to minimize. So there was a lot of design in where you wanted to minimize the number of rounds, and log base 2 of n was too many. Okay, so if you have a trillion key value pairs, which is not normal at this scale, log base 2 of this would be, this might be like 30 rounds, and 30 rounds all of your time would be spent in the overhead of these rounds. That'd be too many. So you want really a constant number of rounds. Okay, so about 3 to 6 years ago, forgetting my timelines, depending on how when you thought this was stable, there was a new system called Spark that came out of Berkeley, and basically this gets rid of the challenge of the rounds being really slow. That's the main contribution of Spark, is it figured out how to get the same resiliency properties without having to write back to disk in between the rounds. Okay? And so now this is part of the Apache distribution that includes Hadoop. There's kind of Spark stuff often distributed with that. And most people are using this because it gets rid of this round overhead for the most part. It does it with some really clever stuff that it stores data structures in memory that can be recovered on the fly instead of having to go back to this distributed file system. So now you can do things like running Lloyd's algorithm directly, and it doesn't kind of run ridiculously slow. Or other like iterative gradient descent algorithms in machine learning, you can run them with Spark, and that's a reasonable thing to do. Something like 40 times speed up is what they were originally advertising. Sometimes more, sometimes less. You know, sometimes they may be a little bit big in the claim, but it was a really big improvement here. So now people use Spark. The round complexity issue is no longer nearly as big of an issue. They still at the back end, the ultimate storage is still often this distributed file system sort of thing. Okay. Yeah.
So for the word count example, you said that they store like the documents 2 or 3 times.
Yeah.
Do you have to account for that in your map and reduce methods, or is that just something?
It kind of handles this automatically. It will pick it. It knows all the locations of all the blocks, and it will pick one of them, typically at random. If it can figure out there's a cluster of them, they were stored randomly, so that shouldn't happen. They might try and figure out not to pull too many from the same computer. Then it knows that one of the computers goes down where the other copies are. If that computer crashes, it rebuilds a new copy, so it's someplace on the active network. All this is in the back end, right? So the beauty of it was you only had to write a few lines of code, and it dealt with all this parallelization, these really nasty issues for you. So it allowed kind of just about anyone to write queries on here, and otherwise it was, an average program could not deal with the complexity of dealing with this parallelization of machines crashing. This was really the key kind of
In what computer did the combining step happen? Did it happen after?
Yeah, it happens the same computer as the map. Think of the map as like a streaming algorithm over the data in a block. And then, but when it's done with the block, it looks at the output queue. Maybe it runs back over that, and it kind of does a sorting step and combines stuff together before that. You might be able to do it kind of on several blocks on the same computer. But that's why I put it as 1.5, because it's really kind of part of one. But you'd write a separate function for it. So really this is the shuffle step that's happening here. And so all of the movement between computers is happening at the shuffle step at this stage. So that's why combining here, I'm sending less data across the shuffle, and I make sure I don't overload on any one of the computers inside the shuffle, after the shuffle. Okay, let's do another example here. This is called the inverted index problem. Again, I've got all of English Wikipedia stored on the DFS. The goal is to build an index, so each word lists all the pages it's on. Okay, so this is like, I wanted to do this for my name, but I want to do this for all of the words. For every word, I want to kind of, like in a search engine, if I search for a word in Wikipedia, give me a list of all the words, right? And maybe each page has stored on it its PageRank value, so I sort them by their PageRank value, right? Right. So again, the map stage, right, is I'm going to so for all words W, for all words W on page P, I'm going to create a word value pair WP. Okay? And then on the reduce step, I'm going to take word page 1, word page 2, and so on, and I'm going to return the word and then the union of these PIs, right? So this is all I did for the inverted index, right? And maybe I wanted to sort, so I can say maybe sort by by their page rank value, or by some other measure that's interesting. That's based on cosine similarity to something like that. Some function here. I could sort these, and this is how I build a search engine. Okay, this is how you build the inverted index. Right, so this was a big operation that Google had to do. One of the two was building the index, the other one was running the PageRank to find the converge to vector. And so MapReduce was really good at this sort of operation. And again, you might want to do a combiner if the word appears multiple times, but but with the word the, you probably aren't going to search with the word the. They might even drop these stop words, the words that occur super frequently. You could, again, do that in the map stage. If it's one of the words that you want to exclude, you can just drop those. That's another thing you can do. Okay? And then I've got another simple example. A little bit more complex. The goal is to build an index on 3 grams, so a sequence of 3 words that appear in exactly 1 page with links to those pages. Right, so the map, again, I'm just going to do a word and the page, and maybe combined, I'm going to do word page 1, word page 2, up to just, or if these are all on the same page, right? So these are all on the same page because I'm reading 1 page at a time. I'll map them just to the same page. So I only count it once. And then on the reduce, I say if the word, if the sequence has greater than 1 distinct page, then I return nothing. Otherwise, I just return the word with a link to the page. Okay, so I can do something a little bit more complex. You kind of start to get the idea, right? All right, and this is instead of a word. Now, word equals a 3 gram. Right, so I scan over the 3 grams of words, and I do this for I create a key value pair for each of these. Right, so it's a 3 gram instead of a word. I should have used G instead. Okay, but that's the basic idea. You kind of start to get it. It's not too hard. Okay, let's quickly talk about MapReduce one more time. Okay, so now, so PageRank. And if you remember PageRank, we're going to be building a, let's say, a probability transition matrix. And I'll call this M this time just to kind of, and you'll see why it's, because P will actually be some slightly tweaked version of this, right, where a column of M, and I'll call this MI, it'll be, it's going to be 0 or 1 over K. So, and this is index of page J that that I links to. So out of K pages. All right, so if it links to K pages, I divide each of them by 1 over K, so it's a probability distribution in this column vector. Okay, and so this is, and this matrix M is kind of the initial version of the probability transition matrix, but this is not going to be ergodic by itself because these you can have these pages which are these dead ends. So you want to, about 15% of the time, once every 7 steps, jump to a random page. Right, so then you have that P this true probability transition matrix is going to be beta, or beta equals, say, 0.85, beta m plus 1 minus beta b. And so now b is going to be, is an n by n matrix where 1 over m everywhere, right? So this is m by m if there are m web pages, right? So this is saying this is jump to a random page, right? And so the key update step is qi plus 1 equals p qi, and I want to run this like 50 times. So I want to start at some, basically the uniform distribution over pages, and I want to run it 50 times, and then the 50th state will be representation of my convergence states, right? So this will be equal to beta m plus 1 minus beta b qi. Okay? And so this was the other big computation other than building the inverted index that Google commonly had to do. And so they wanted to do this in MapReduce as well. So how do we do this on MapReduce? All right, so how would we do this on MapReduce? So think of a block as a set of web pages, right? Which is equivalent to a set of columns of m. Okay, and so then I'm going to do 50 rounds of MapReduce, and each time I'm going to process the Q vector by each block. So I'm going to send the Q vector out. So in map, I'm going to have a block which is going to have m from columns from A to B, and I'm going to have the query is described by the whole vector qi. Okay, so first I restrict qi to only the range from A to B. So only the web pages in the range from A to B that maps onto the columns from A to B. And now I'm going to do qi plus 1 kind of here. I'm going to output this as well. The key here is not so important, but my qi plus 1 coming out of this block is going to be equal to m a b times qi a b. Okay, so I'm going to process MAB inside of by in here, and this is going to correspond with this part of the matrix of the transition here, but only on those columns. Okay, then in the reduce, I'm going to set qi plus 1 is going to be equal to beta times the sum of I equals 1 to n of all the qi plus 1s from, I shouldn't use I again, let's use j, right? From each of the nodes, I'm getting all of these vectors as my word and the key value pair, right? So I'm only just roughly send this to one place where I can do this distributed across where all the data is. I can do it multiple times. I'm basically adding together these multiplied times beta plus 1 minus beta times the 1 over m vector. Right, so this teleportation step I can just do in the reduce phase, as well as the downweighting here, and I add together all of these steps. Right, and this replicates what's going on in the matrix multiplication by doing it by the columns themselves. Right, and each column is a web page, so it shouldn't have too many links on it. The average web page has like 20 links on it on average. So I can do this, I can break up a bunch of columns inside of each block. Right, and okay, I need to do, you know, maybe on each node I know which blocks are relevant, which web pages are relevant, so then I would only need, if I know I'm only locally computing that part, I only need to compute that part of this vector, the associated rows of this vector, which will then be kind of reused here. But I've sent this data, what's gone in the shuffle step, this is the part which is going across the line for the shuffle. And this is maybe sent to all of the different nodes to recalculate and get a local copy of Qi plus 1. Okay, so I can fit this within MapReduce. So if I see an example here, this is an example M matrix, right? So this is one web page. Okay, so, and each column is one of the web pages. What I can think of is I can stripe it so that each web page looks like this. And I only need to store the non-zeros. So it's actually, I don't need to store all the zeros here. So for instance, this web page, this one is only stored as this. I don't need to store so much here. Right, so then when I multiply a Q vector by this, I just, you know, each of the blocks, I can think of each of these as the blocks, or it could be a set of columns in a larger example. I just look at this, I look at the relevant part of the Qi vector, and I multiply it by this one here that's stored in the, I guess this should be stored in the second coordinate, not the third coordinate. Right, but, so I just look at the corresponding coordinate, and I multiply it by 1, it updates all this way. So I can do this in like a sparse manner pretty easily.
Also number 4 should be 1 and 2.
Yeah, okay, I copied these over quickly before the lecture. This is, and this should be 2, and this is 1 and 3. Yeah, so there seems to be some typos in here. Okay, but you get the idea. You can store it in a sparse format. So I can store a number of these web pages on here and do this reasonably efficiently. Okay, so there was a question yesterday. What if Qi is too big for one computer? There are situations where this occurs. It was possible at some point on really cheap machines that this would have been the case with MapReduce. Nowadays, I think you can typically fit Qi on a large enough computer that they would run this on. But if not, what you would do instead is you would break these up into different sorts of blocks, and this has some other sort of advantages, where the blocks now correspond to things like this. And now I don't need to store the whole Qi for each block. I only need to store the part of Qi that corresponds with the input and output. And if you do enough of these blocks, if you have m computers, you have square root m by square root m. I'm storing 1 over square root m times 2 for the input and the output fractions, or 1 over square root m of the Qi matrix in each of whenever I need to process a block. And so at that stage, you can always store the relevant part. You need to be careful how you pass this around. Okay, so you can, so if the size of the vector is too big, then you need to do kind of a blocking instead of a striping of the matrix. And these are techniques that have existed in parallel algorithms for matrix computation for a while, but they kind of map into the MapReduce. Okay. So we'll end there. We'll have one more lecture on graphs where we're talking about communities and detecting kind of important nodes beyond PageRank, some other kind of things about understanding kind of social structures on graphs on Wednesday. And that'll be the final lecture before the end term test. So, and if you want to, again, look at example posters, because you need to start making yours for your project. There are some up front here. You can come look at them. Hey. Oh, great.